Let's take a look at a reaction that you're familiar with on the microscopic scale and see if we can see what really happens when two molecules react. As an example, let's look at an SN2 reaction. Here we have an sp3 hybridized carbon atom with a good leaving group, an electron withdrawing group, which makes this carbon electrophilic. We have a nucleophile, and when the nucleophile and the electrophilic carbon, collide, we can form products where we form a bond between the nucleophile and the carbon, and the leaving group breaks the bond to the carbon and leaves. There are a couple of things we can notice right off the bat. A collision must occur between the nucleophile and the electrophile, and the orientation of that collision matters. If the nucleophile collides with the electrophile on the side where the leaving group is attached, you would not expect any reaction to happen because the nucleophile cannot make a bond to the electrophilic carbon. However, if the nucleophile attacks from the back side, then we can form a bond between the nucleophile and the electrophilic carbon, kicking off, breaking the bond to the leaving group. Now let's take a look at what happens to the energy when this reaction occurs. Initially, we have vibrational kinetic energy and translational kinetic energy in our reactants. When the nucleophile approaches and reaction begins to happen as the collision occurs, the leaving group carbon bond is stretched and the geometry, sp3 geometry around the carbon atom is changed to a trigonal bipyramid type of geometry. We now have non-optimal bond lengths between the leaving group and the carbon and the nucleophile and the carbon, and a very non-traditional geometry about the carbon atom. Thus, this configuration of reactants has a very high potential energy. During this reaction, the total energy available to my molecules has not changed. What has happened is I've gone from a high kinetic energy, low potential energy state to a high potential energy, low kinetic energy state. So I have transformed kinetic energy into potential energy to get to this highest energy point, or the transition state for the reaction. Nearly all reactions have some type of potential energy barrier where kinetic energy is transformed into potential energy in order to form products from our reactants. This potential energy barrier is what you know as the activation barrier for the reaction. Once I have formed the transition state, then I can either reform reactants by reforming the leaving group carbon bond and stretching the nucleophile carbon bond, or I can form products by forming the nucleophile carbon bond and stretching the leaving group bond until it breaks. When I form products or reactants, I go back to a low potential energy state, and I gain kinetic energy of translation in my products and kinetic energy of vibrations in my products as well.